Okay, people, let's do a brief review of the difference between reflection, refraction, and diffraction. So I expect this will be largely review, but it will put us in a good position to understand some of the more nuanced techniques in spectroscopy. So the first one to discuss, reflection, the change in the direction of waves when they bounce off of a barrier. And we can see here the law of reflection states that when we have a fully smooth surface, our angle of incidence will match our angle of reflection. So that's what the I and the R stand for. So incidence and reflection. Okay. So, and when we have this like perfect idea here where the angle of incidence matches the angle of reflection, we call that specular reflection. And as you can see right here, this is actually a picture of Mount Shasta. And here you can see this lake was very calm, a very windless day, meaning the surface of this water was like a mirror, like mirror smooth. So what we are seeing is the specular reflection off of that lake to give us this mirrored image. Now, if you've been around the mountains and around the lakes, as the wind picks up in the day, you might recognize that the water gets choppier and you're not able to see that mirror image anymore. And that's what we refer to as diffuse reflection. Or maybe not even in this case of seeing a mountain reflected in a lake, but perhaps some roughed like surface. If you take sandpaper to a mirror, for example, you still have all of these various laws of reflection here. So for example, if I point out this little feature, we still have the angle of incidence matching the angle of reflection, but that has to be normal to the surface that it strikes. And if there's not like this atomically smooth surface, we're going to get all of these different stray beams not making it right back to our eyeballs. So thus, we won't see this nice, mirror image of the mountain when the lake starts to get a little choppy. So that's reflection. So refraction is the change in the direction of waves when they travel through different media. So for example, we use this value n as the index of refraction. And that value is known for various media, whether it's air, liquid, or vacuum. And the idea is light will actually travel at a slightly different speed through different media. Typically, it will travel slower through more dense media like a liquid versus media that has no density at all like a vacuum. So I'm not going to spend a whole lot of time here making us go through Snell's law, but as you can see, the angles of incidence and the angles of refraction will arbitrarily be, or not arbitrary, but will be based on the ratios of the indices. So a couple cool things happen as you start to pitch out this angle theta. So at a certain point, you'll get to what's known as the critical angle, and this makes some very cool optical illusions. You can like make an object almost look like it's disappearing. If you've got an object submerged in water and you rotate it such that you are looking at the critical angle, you might not be able to see that object anymore. So that's an optical illusion. And we can get a similar optical illusion from the total internal reflection, where now truly we will have angle of incidence matching the angle of reflection. So this is a really cool phenomenon in various forms of spectroscopy. So moving on, diffraction, the change in directions of waves when they pass through a small opening or around a barrier in their path. So this is where we use this technique, or we use this phenomenon in microscopy. So there is less diffraction when the length of the opening is greater than the wavelength. There is more diffraction when the length of the opening is less than the wavelength. So this is how we can get a crystal pattern. You might have heard of X-ray crystallography. So that spacing then would represent like the space between atoms or the space between molecules in a crystal structure. And based on the direction of these waves, and our ability to detect them in space, right, depending on where we detect them, will give us a diffraction pattern that we can eventually relate to a crystal structure. So another technique in which we take advantage of diffraction is in a grating. So if we look macroscopically at a grating, it might look like this smoothed surface. But if we were to zoom in on this, we can see that they have teeth, typically given by a spacing d from like the center of the tooth to the center of the tooth. And this is diffraction because now these teeth kind of operate like barriers that light has to travel around. So another cool phenomenon happens with this. Depending on the angle of incidence and the angle of the diffracted light, we can get a color change, assuming that we have all of the wavelengths of light incident on our grating. So if we have a white light source, for example, we can get the specularly reflected light, which will be all of the wavelengths. But if we change the angle at which we observe, we will see different wavelengths. And I'm not going to spend a whole lot of time getting into this equation. The idea here is it's based on the fact that our waves must be quantized. Like we have to have integer values of the wavelength. So that's an integer. We can't chop up our wavelengths into these like non-integer units. So the way this the grating equation goes is the length CB. So this is normal to A, and then here we have the line out at 45 degrees. And this length CB to BD must be some integer wavelength. And so solving through these equations, we could see how we could get different colors based on a different angle of incidence. Okay. And so we take advantage of these in typically in visible spectroscopy, where we want to separate different wavelengths of light to be used to record a spectrum. Okay, folks, that's all I got for this one. I will see you in the next video.